row address decoding now. So while we say that there are, let us say 128 rows, or in this case, for example, I'm saying 512 rows, decoding, as you can easily understand, essentially means that I am putting a NAND gate, for example, that okay, all these addresses for selecting word line 0, A0 has to be 0, A1 has to be 0, and so on. Or for selecting word line 511, all the 9 address bits have to be 1. So I have to either use a NAND gate or an OR gate or something like that, so that I can make my decoder. How to make large width decoders, we already saw in DVD also, but we can actually say that okay, we make large decoders by splitting it into 2 stages. Okay, what could those 2 stages be? Those stages could, the first stage is called pre-decoding, the second stage is called post-decoding. Now, at any point of time when we start to decode, we would, for example, in this, decoded A0 to A0 bar and A0. So this is A0 bar and A0 buffered. But what do you realize that I have not connected A0 input directly to my NAND gates? Why did I not do that?
Because of load.
Yeah, because I cannot really show a big load onto my external pins.
Yes, sir.
So I buffered them. So even if I needed A0, I buffered it and then used inside my design. So we essentially need to design a n is to 2 raised to power n decoder. If n was 2, then each of my NAND gates is 2 input. But I need 2 raised to power n NAND gates. Are you able to see this? Hello?
Yes, sir. Yes, sir.
Now, if this n was 9, as in 9 is to 512 decoder, this would mean we're talking about 512 decoders, and each NAND gate is 9 stack long. That is not something that you want, and that is what we are saying, that we pre-decode. We pre-decode such that if there are more address bits, for example, if we have 4 address bits, we do first level of decoding through first set of gates, and the second level of decoding through the second set of gates. Who will explain this slide to me? What is happening here?
So, like, I can what I'm able to see is that they're kind of like 2 to 4 pre-decoding happening, maybe.
Good.
But after that is not evident. I mean, then it is going to the maybe kind of this below structure is kind of a like pre-decoding, and above is the NAND gates is kind of like post-decoding, maybe.
Yes. Good.
And since there are 8 kind of, after pre-decoding we have kind of 8 lines.
Yes.
Okay. But there are 4 bits. So it cannot be, yes, it is like kind of 2 to maybe 2 pre-decoding we have like 2 to 4, and maybe 2 such kind of pre-decodings, but
okay, so we have 2 buses of pre-decoded addresses now. Okay, and in the post decoder, we simply merge these 2 buses. So to select row 0, what did you need? You needed that A0 should be 0, A1 should be 0, A2 should be 0, and A3 should be 0. So if I connect this as one of the inputs, I am ensuring that A0 and A1 are both 0. Are you able to see this? And for the other input of this NAND gate, I have connected this line. I have ensured A2 and A3 are also 0. So I've used only 2 input gates at both the places now. And I have a 4-bit address decoding available with me.
So can you please just explain this again? This A1, A2, this tapping at this above stage, the
So
black tap.
what is this one? What does this line represent? When will this line be selected? When A is equal to 0 and A1 is also equal to 0. Is it not? If either of them is 1, this line will go to 0.
So this first line will be selected when A equals to 0 and A1 equals to 0. Yes, sir. Yes.
Look at the connection of this NOR gate. Na? How is this NOR gate connected? If you look at the first NOR gate, it is connected to A0. A0 is one input, A1 is the other input. Only when
Yes.
both of them are 0 will the output of NOR gate be 1.
Yes, sir. Yes.
Similarly, look at this one now. Only when both A2 and A3 are 0 will the output of this NOR gate be 1. That is where this line represents
Yes.
A2,
Yes. Yes.
A2 bar, A3 bar. This line represents A0 bar, A1 bar.
Yes, sir.
Now, you have merged, or for this NAND gate, you took these as the inputs. So what happens when I have chosen A0 bar, A1 bar and A2 bar, A3 bar as the inputs for a particular NAND gate, this NAND gate will give an output word line bar or row 0 bar when both of these set of inputs are, all the 4 inputs are 0. I will simply buffer it subsequently and I will have my word line.
Yes, sir. I mean, so when A0, A1, A2, A3 will be 0, then I will have this R0. Yes.
Yes. This is called pre-decoding. And this is called post-decoding. What I have essentially done is, by splitting my overall decoding operation across two levels, I have reduced the stack size of my gates there. My designs will be faster and I will be more area efficient also probably. Are you able to see this?
Sir, I have a doubt, sir.
Yes, please ask.
Sir, here, why are we using active low word line select, sir?
Active low word line select, where?
No, because if we are selecting R0, the row 0, then the row 0 is going to 0 instead of 1.
Yeah, so word line will be after, like this NAND gate output will be buffered and I will get the word line. Na?
Achha, okay, so you buffer it through a inverter and then do the word line.
You are a designer. See, you have to see how these gates can be minimized. Are you able to see the inputs of these gates is load to these NOR gates?
Yes, yes.
Remember the discussion on logical effort in DVD?
Yes, sir.
So those of us who are attending MDT and did not attend the DVD course, I would recommend that you watch the lecture of logical effort in the DVD course. It's also available on the YouTube channel, and it can bring you up to that. We discuss exactly this thing as to how to size different stages so that you have the best delay. So now all that we're talking about is size these two stages such that you get the best delays. Are you able to see this, Ranjit?
Yes, sir, I understood that. Sir, one more thing is that, are these connections programmable?
Yes, we'll come to that. They are programmed. We will come to how they are programmed.
Okay, sir.
But you can obviously already see a trend here, is it not?
Yes, sir.
That for some rows, when this is getting selected, these will be dots here and so on. So we will look at it in a little more detail later.
Sir,
Yes.
if you would have not used this kind of scheme for the decoding, then I would have like 4 stack NAND gates and total 16 NAND gates, right?
Hmm.
Okay. So not only able to reduce the stack and also able to reduce number of gates also maybe.
Yes,
Okay.
in this example, you may not see that reduction as much, but overall you will see that the overall gate size and everything is reduced. So when you do the logical effort analysis, you will see there's a significant gain of going through splitting this gate through 2 stages. In fact, we did that one example of designing a 8 input AND gate in 1 stage and 2 stages and 3 stages in DVD. So just that exactly the same thing that example was a precursor to this discussion that we wanted to have here.
Okay, so the only difference that we are kind of dividing different stages using different kind of gates, like maybe not this.
You could have made that AND gate also like this. Doesn't
Okay.
matter.
Hmm.
You know how to do bubble pushing. That was taught to you much earlier.
Yes, sir. Right. Yeah.
Okay. So now how to do this pre-decoding? Should we also only use 2 to 4 pre-decoders, or should we use 3 to 8 pre-decoders and all that? See, these are important design decisions that you will have to make as a designer. Let us say you have a 10 input address bus. So if you have a 10 input address bus, what happens? You obviously cannot make 10 input NAND gates. Can you? No. At most, you may want to go to, let us say, 4 input NAND gates. If you want to go to at most 4 input NAND gates, then how many pre-decoders do you need to put in your system? If maximum NAND gate stack has to be 4, how many maximum pre-decoders can you have? If you want to do single stage post decoding.
So originally I have 10 bits, sir.
How many, however number of bits you have originally, that doesn't matter. How many pre-decoding groups can you have if you have 4 input NAND gates at the post decoding? If my final NAND gate can accept 4 inputs, how many pre-decoding groups can I have? How many pre-decoders can I have?
I think 4, sir.
Yeah. See, in the previous case, we had 2 groups of pre-decoders. One was pre-decoding A0, A1, and the other pre-decoder was decoding A3 and A2. So we had a 2 input post decoder. If we can have a 4 input post decoder, it means that we cannot have more than 4 pre-decoders there. Now you have 10 address bits. You have to distribute them amongst these 4 pre-decoders. How would you distribute them? Would you make 3 pre-decoders of 3 to 8 and 1 pre-decoder of 1 to 2? Or you will make 2 pre-decoders of 2 to 4 and 2 pre-decoders of 3 to 8? What would you do? Yes, Faisal.
So actually, I'm not getting the concept. Like in the previous example, can you please show the previous example? So here we are decoding 2 to the power 4 rows. Am I right? Or
yes.
And to reduce the stack, we are doing pre-decoding and then post-decoding.
Yes.
Okay. Okay, sir.
So what was your question, Faisal?
So I was not able to get this part only. Then you have changed the slide, and that's why.
Okay. So now, how would you distribute these 10 address bits? In the previous example, we distributed into 2 blocks, A0, A1, and another block of A2, A3. Now you have 10 address bits. How would you club them? You could do 3 to 8 decoders and 1 to 2 decoders. That would take care of 10 address bits. Or you could do 2 3 to 8 and 2 2 to 4. Which one would you prefer?
Sir, or we can also do the
I
5
think
2 to 4.
second one, sir. I
5
think
2
it
to
would
4
be
I said
better.
is not allowed because your NAND has only 4 inputs. Your NAND will not function then. I've already put in a constraint of 4 input NAND gate.
Oh yeah, yes sir.
If I had not put that constraint, your answer is right. But over here, I've already put that constraint. Yeah, someone was saying something.
Sir, can we put 2 to 4 pre-decoder 5 times? I think that overall output lines would be 5 into 4, 20. And if we see the second case, sir, 3 to 8 pre-decoder, it would be 16, and 8, it would be 24. So, sir, overall the area would be lost here, I think. If our in post decoder the number of lines increases, then I think area would be wasted.
Good. So you're saying there are 24 lines over here. There are 26 lines over here. And if we had 2 to 4 decoders, 5 of them, we would have been able to work with 20 lines. Absolutely right. However, I've already put a constraint that you can have only 4 input NAND gates. So what to do?
Then, sir, second case would be, I think, better.
Because it is denser. Or is there any other reason?
Sir, I have a doubt. I mean, if we choose any of these two implementations, my post decoding is basically fixed. Then I'm choosing the pre-decoding. That is the question, right?
Yeah, over here I have fixed it for you that you cannot go for a NAND gate with a stack more than 4.
So I have fixed the post decoding that it will be 4 input NAND gates.
Yeah.
Okay.
So do you already see that if I use different kinds of decodings, there is a different area that we are talking about, given by number of lines. But there is also different kind of power that we are talking about. If there are more lines, it means every line has lesser load. Since every line has lesser load, then what happens? The power consumption reduces. Load reduces means speed can also improve. So the speed, the speed is a mix of two things. The speed is a mix of how fast the pre-decoding is, and then secondly, the load on the pre-decoded outputs, because that would define how fast the post-decoding can be. Only pre-decoding impacts or can impact probably setup time. Post-decoding would typically be a part of excess time, because that is where you will mix clock to address. Okay. Are you able to see all the three trade-offs happening in the address decoding domain now? We looked at the number of address lines, that is area, power. If there are, if you use big pre-decoders, then lesser number of lines would toggle, and therefore power would reduce. And smaller pre-decoders can mean faster setup times, but because there are more number of lines and a long stack post decoder, overall post decoding may be slower.
Sir, what is this point of 1/8 of row decoder? So this point, can you say 3 to 8 pre-decoding?
Yeah, so if I have done 3 to 8 pre-decoding, how many row decoders, how many post decoders will I connect to any one output? So you see over here, each output of these post decoders like if I consider this bus of the first pre-decoder, only one of the outputs of my pre-decoder connects to any one row decoder, any one post decoder. Are you able to see this?
Yes,
I
sir,
cannot
one out.
have both A0 A1 bar and A0 bar A1 bar connected to this NAND gate. Only one of them will connect at any row. In any row, only one of them will connect. Are you able to see this? So if I have a pre-decoder which has 8 outputs, each row will connect to one of those outputs. So the total number of outputs, total number of connections that any output would see would be rows by 8. Are you able to see this now, Raghav?
Sir, you're talking with the output R0, right?
These outputs.
Oh, okay.
Outputs of the pre-decoder.
Okay.
Okay. So that's what is meant by this. Anything else?
Sir, actually, if I'm say more number of rows are there, so but sir, load becomes more, right? There are more rows now.
More rows?
Because
Kyun? We just said there are 1K, 10 address bits, so there are 1K rows. Whether I use 3 to 8 pre-decoder or 2 to 4 pre-decoder, that is all. That is the comparison I'm doing now. For any instance, the number of rows is already established. We know how many rows we are talking about.
Hello, sir.
Yes.
Sir, is there some constraint that we are supposed to do this decoding only in the 2 stages, the pre-decode and the post-decode? Can we increase the number of stages?
We can. For example, when it comes to pages, then we would anyways have another stage which would decode the page.
Exactly.
Yeah, so we can. So if you really want to use 5 2 to 4 pre-decoders, then you can use two-stage decoding at the post-decoder also. It will only increase delays.
Sir, but if we increase the number of stages, the delay should decrease, no, sir?
Depends. Again, logical effort result.
Logical effort, yes, sir.
So there is an optimal number of stages that you would want to keep.
Yeah, true.
So you arrive at that. No problem. That is what we will use.
Okay, sir.
So in the course project, some of the teams would be involved in designing these decoding, address decoding. So you will have to do this logical effort analysis and arrive at a appropriate architecture there. Okay.
Okay, sir.
Sir, one more in last slide, sir. There are, I think, there are three kind of connection here in the fifth vertical line, fifth NOR gate output. So would it create any kind of I think would it create any problem in this architecture, sir? I didn't get it, sir.
I have not even shown any connection to the fifth NOR gate because I have only shown 3 rows, R0, R1 and R3. For them, we know that the fifth one, the fifth output has connections for 4 of them. Yes. So what's the problem there?
Sir, there are 3 connection to the row for 3 AND gate. So at same time, 3 AND gate would take the input from that fifth NOR. So would it create any kind of race condition or it would increase the capacitance load on the NOR 5th NOR outputs?
So see how many outputs or how many row decoders will that gate 5 be connected in total?
Sir, is it 4?
Yeah. So total it is 4 only.
Yes.
Okay.
Whether they are connected first, like as soon as you have the row 0, row 1, row 2, row 3, whether they are connected there itself, or for example, for the last NOR gate, they will be connected for row 12, 13, 14, 15.
Okay.
Wherever it is connected, the capacitance is going to be the same now, Prince.
Yes, sir.
In this example, because I was showing the first few rows, A2 bar, A3 bar connection was connected everywhere. But otherwise, all will be connected only 4 number of times. The load will be same across all the 4.
Yes, sir. Yes, sir.